Hi guys, welcome to the Support Vector Machines lecture using Scikit-learn in Python. As suggested in the theory lecture, we are going to work with the breast cancer diagnostic dataset in this lecture. As you already know that this dataset is available on Kaggle and originally belongs to UCI Machine Learning Repository. The dataset was donated by Nick Street in 1995 for the public use. Relevant papers and detailed description on the dataset is provided at UCI website. Because we have worked with this dataset in logistic regression and KNN sections, so this will allow us to compare the SVM to those models. However, in the SVM project lecture, which is going to be the next lecture, we will work with another new and real dataset on credit approval. Breast cancer dataset can be loaded from Scikit-learn, and it's up to you if you want to load from Scikit-learn or you want to use the CSV file which is provided in the course material. I am going to load the one which is in the course material. So let's move on to the new Jupyter notebook and learn by doing. So the first thing first, we need to import some libraries. So import pandas as pd, import numpy as np, import matplot. You can always press tab for autocomplete. So import matplotlib.pyplot as plt, and we also need cborn. Import cborn as sns. And finally, we need to set matplotlib inline. Matplotlib inline. And let's run this cell. So we have imported all the required libraries. So let's move on and read the CSV file in df. So df is going to be pd.read CSV. So the CSV file name is breast_cancer_diagnostic.csv. You can press tab for autocomplete, and if the file is in the folder, you will get the name autofilled. Let's run this cell, and as always, let's check the head of our data frame df. So df.head, and here we have ID, diagnosis, mean radius, texture mean, and a couple of other columns. So in total, we have 33 columns. Let's add few cells and call info on our data frame just to get the summary on our data frame. So df.info, and run this cell, and here we have 33 columns, and this is complete data set and 569 entries. And if you notice, you don't find any null value in the data set. Once again, I want to mention that we will only consider 10 real valued features in this project for diagnostic. Let's move on and separate those 10 real valued features along with the diagnosis column. I'm going to copy the list of those features from the reference notebook and pasting here. So we are grabbing radius mean, texture mean, perimeter mean, area, smoothness, and a couple of other columns along with the diagnosis column. And we are displaying the head of our data frame. Let's run this cell, and here we have our data frame with 10 real valued features that we are going to work with. So moving forward towards the exploratory data analysis, we are already familiar with the breast cancer dataset, so we can save some time in EDA. Let's have a quick look on the pair plot and instances in each target class using value counts. We can call pair plot using cborn. So sns dot pair plot and pass in df, and let's pass in hue, which is going to be our diagnosis column. So we can copy this here and paste it here, and let's run this cell. This will take some time because we have a relatively bigger data set. So here we have our pair plot. We see blue and green points because of hue, where cancer is malignant and benign. This is very small, but still we can see that M is for blue and B is for green. Let's have a quick look on the number of instances in each target class, which is B and M, using value count. So we need to grab diagnosis column and call value counts and run this cell. And here we have 357 B type cancers and 212 M type of cancer. As we have already worked with this data set in the previous sections, so I'm not going to do more exploratory data analysis. However, I recommend you to explore more so that you understand your data before you move on to the machine learning section. So let's move on towards the machine learning section. And the first thing what we do, we call train test split. I'm sure all the steps regarding machine learning are on your fingertips now. So let's import train test split from Scikit-learn dot model selection import train test split and run this cell. We need to separate features and target column. So uppercase X is our features. So we can call df dot drop, and we don't need diagnosis column in the features. So we can drop diagnosis column. And axis is 1 because we want to drop along the axis. And what we are dropping in features, that is what we need in Y, which is our target. DF and diagnosis. So let's run this cell. And now we have features in capital X and our target values in Y. Let's split the data into train and test dataset. So train, test split, press Shift Tab, and just to save some time, move down and copy the 2 lines of code from the document string. So copy here, paste this code, and let's change the test size to 30% and leave random state as 42, which is default value. And let's run this cell. So now we have the train and test datasets as well. To move on, we need to import support vector classifier. Support vector classifier is under SVM. So we need to do another import from sklearn.svm import svc. So support vector classifier with capital S, capital V, and capital C. Let's run this cell. And the next step is we need to create an instance for svc. So svm underscore m equal to svc. And if you press Shift Tab, there are range of parameters that you can play with. We will come back and discuss some of very important parameters at later stage, but at the moment, let's create an instance using the default parameters. Now we have svm underscore m as instance for support vector classifier. We need to train our model, so svm underscore m, and for this purpose we need to call fit and pass in the training dataset. So x underscore train and y underscore train. And let's run this cell. So we have trained our model now. We see that there are a number of parameters such as C, degree, gamma, and kernel. We will come back and look at them in a while. Let's keep the default at the moment to keep the things little simpler at this stage. Let's move on and do the predictions now. So pred is going to be our predictions. We have trained our model svm underscore m. We need to call predict and pass in the test dataset. And let's run this cell. So now we have predictions for our test dataset in pred. Let's add few cells and move on towards the evaluation. For evaluation purpose, we need to import classification report and confusion matrix. So from Scikit-learn dot matrices import confusion matrix and classification report. Let's run this cell to do these imports and use print function to print confusion matrix and classification reports. So print classification report and pass in, if you press shift tab, we need to pass in y true and y pred. So these are the values what we know and these are the values what our model is giving. So this is y test and these are predictions which are in pred. Y test pred. Print confusion matrix and pass in y test and pred, and let's run this cell. So here we have our classification report and confusion matrix. If you see at the results 0.6968 and some misclassification, true positive and true negatives, the model is not very bad. But if you remember, we got very good results in the previous sections using other models such as logistic regression. SVM or support vector machines should do much better than what it is doing now. We need to adjust some parameters, and finding the right parameter is very important. Let's move on and explore some of the important parameters in SVM. Starting with the kernel parameters, different kernel functions can be specified for the decision function. Common kernels are linear, polynomial, RBF, or sigmoid. It is also possible to specify our own custom kernel, such as we can give the kernel as a Python function and so on. However, RBF, the radial basis function kernel, is the most popular kernel function and is commonly used in support vector machines. The parameter C, which is common to all SVM kernels, is a penalty parameter for the error term. The parameter degree is a degree of polynomial kernel function and is ignored by all other kernels. Another very important parameter is gamma, which is a kernel coefficient for RBF, polynomial, and sigmoid. Let's move on and talk about the default RBF, the radial basis function kernel, which is probably the best one to use. The RBF kernel on two samples x and x bar, which are represented as feature vector in some input space, is defined by the given equation, where x minus x bar with square may be recognized as the square Euclidean distance between the two feature vectors x and x bar. And the keyword gamma must be greater than 0. When training an SVM with RBF kernel, two parameters must be considered, C and gamma. The parameter C, which is common to all SVM kernels, trade off misclassification of training examples against simplicity of the decision surface. A low C makes the decision surface smooth, while a high C aims at classifying all training examples correctly by giving the model freedom to select more samples as support vectors. The parameter gamma defines how much influence a single training example has, like how far the influence of a single training example reaches, with low values meaning far and high values meaning close. The gamma parameter can be seen as the inverse of the radius of influence of samples selected by the model as support vectors. Let's move on and try to understand the effect of C and gamma using simple dataset. Consider we have a dataset with green and red points as shown in the scatter plot. We can say green for true or 1 and red for false or 0. We want to train our SVM classifier. Let's see how gamma and C works on this given dataset using RBF kernel. So let's see the effect of gamma first. The behavior of the model is very sensitive to the gamma parameter. When gamma is low, the curve of the decision boundary is low, and thus the decision regions are not very good. For the very low value of gamma, the model is too constrained and cannot even capture the complexity or shape of the data. When gamma is high, the curve of the decision boundary is high, which creates islands of decision boundaries around data points. So, for large value of gamma, the radius of the area of influence of the support vector only includes the support vector itself, and no amount of regularization with C will be able to prevent overfitting. The parameter C trades off misclassification of training examples. For the low value of C, we see our model or classifier is tolerant to misclassification, whereas for the high values of C, the classifier is working hard not to misclassify the data points. Hence, the model is not generalized to the test dataset, and new points might be misclassified. So, moving forward, the conclusion is we need to get the best value of gamma and C to get the best from our trained SVM model. Although it is tricky but very important to find the right parameters so that the model works at its full. Grid search is a common way for this purpose. We create a grid of parameters and try all the possible combinations to see which one works the best. Scikit-learn has a built-in capability to implement grid search with its grid search CV module, which is great and simple to work with. Important members of grid search CV are fit and predict. Grid search CV takes a dictionary and the grid of parameters is defined in that dictionary, where keys are the parameters and values are the setting to be tested. Let's move on to the working notebook and try to find the best value of C and gamma using grid search CV. So the first thing to implement the grid search is we need to create a grid of parameters, which is a dictionary. Let's create a grid of parameters now. So PARAM param grid equal to dictionary, and we want C as a key and pass in the list of values, and we want to test 0.1, 1, 10, 100 and 1000. And the second parameter we want to find the value for is gamma, and pass in the list of values that we want to test 1, 0.1, 0.01, 0.001 and 0.0001. Let's run this cell. So these should be curly brackets here because we need a dictionary. And let's rerun this cell. And here we have a grid for the parameters C and gamma. To implement grid search, we need to import grid search CV, which is a part of model selection in Scikit-learn. So from Scikit-learn dot model selection import. We can press tab for autocomplete and run this cell. So we have imported grid search CV with capital G, capital S, and capital C and capital V. We need to create an instance for grid search CV as well. So let's create its instance. So grid equal to grid search CV. If we press shift tab, we need to pass in estimator, param grid. This is what we have created here. Estimator is going to be our SVC estimator, and we can pass in verbose as well. It controls verbosity. The higher the value is, the more messages you will get in the output. If you don't pass anything here and leave it as default, which is 0, you will not see any message. It is always a good idea to see some output. Hence, it's good to pass some small number. We can pass in 2 here, and we will leave all other default. So let's pass in estimator, which is SVC, and the grid of our parameters that we are going to test, and verbose. Let's pass in 2 here. Another important thing that I want to mention here, and you need to know about grid search CV, it is a meta estimator. It takes an estimator like SVC here and creates a new estimator, which is grid here, that behaves exactly the same way as SVC classifier. So let's run this cell, and now we have a new estimator grid, which will behave the same way as SVC. So just like any other model, we can call fit on grid and pass in the training data. The fit in this case does little more than the usual fit in other models. First, the fit finds the best parameter combination by running same loop with cross-validation, and later on, after getting the best parameters, it runs fit again on all data passed to fit without cross-validation. It then built a single new model using the best parameter settings. Let's call fit on grid and pass in the training dataset. So let's add few cells, and grid dot fit, and our training dataset is X train and Y train. And let's run this cell. So you see this output here. These messages you are getting because you have set the value 2 here. So if you move down, so these are the parameters for your trained model now. If you want, you can check the best parameter combination, because after running this grid search, now you have the best combination of gamma and C. Let's check what are the values of best parameters C and gamma. We can call grid dot best param and run this cell, and these are the best parameters that the grid search has found for our training dataset. So C is 1000 and gamma is 0.001. We can get the best estimator as well. Simply call grid dot best estimator and run this cell, and this is our best estimator. We can check the score for these best parameters as well. So grid dot best score and run this cell, and here we have the score. So moving forward, we got the best parameters and the best estimator. We need to do the predictions and evaluate our model now. Let's add few cells. So grid underscore pred is equal to grid dot predict and pass in the test dataset, which is x underscore test. Let's run this cell, and now we have predictions from our best classifier with the best C and gamma parameters in grid_pred. Let's print confusion matrix and the classification report. So print confusion matrix, pass in what we know, which is the observed values, y, test, and grid_pred. Let's copy this line and paste again and change confusion matrix to classification report and run this cell. So here we have the results with the best parameters and best classifier. We can see that the results are way better and improved with the best parameters. Now you can imagine the importance of grid search for support vector machines model. You may not be able to get an idea about the best values of your parameters, C and gamma in this case, without using grid search process. Keep it in your mind that the grid search can take really long time, especially for the large data sets and bunch of parameters. It also depends upon your computer power as well. The best way to implement grid search during the real-life data projects is to set things up after cleaning the data. Do the grid search on smaller set of grids, for example 1, 2, or 3, to make sure that it works correctly. Once you see that the things are working, then set it on full set of parameters with as many values as you want in the list for each of your parameters. In this way, you will save time and you know it worked on small set and will possible work on the full set of parameters. It will take time and you can do something different. So with this advice, we are done with SVM lecture. Let's have a quick overview on the lecture. So the first thing, we imported the important libraries and read the breast cancer data in DF. We displayed the head info and selected the 10 real valued features to work with. Then we moved on and created a pair plot using Seaborn and counted the target values for B and M type of cancer. We moved on towards the machine learning and imported train test split and separated the features and the target column. Then we did the train test split and moved on to the support vector machine classifier. We imported support vector classifier from Scikit-learn.svm and created its instance. Then we trained our model svm_m using fit on the training dataset. And we used default parameter in this case. We moved on and did the predictions and printed the classification report and confusion matrix. With the default parameter, we have seen that our model did not perform very good. And then we moved on and created a grid for C and gamma parameters with the list of values that we want to test. We imported grid search CV module from model selection in Scikit-learn and then created its instance. Then we moved on and called fit on grid, passed in training dataset, and find out the optimum or the best value for C and gamma. And here we got the best values for C and gamma. We got the best estimator as well, and then we checked the score as well. Moving forward, we did the predictions and passed in the test dataset, and then printed the classification report and confusion matrix. After implementing grid search and finding the best parameters for C and gamma, we have seen significant improvement in our model. The model has performed very well with the optimum value of C and gamma. So guys, this was all about SVM at the moment. I recommend you to go through this lecture once again and try to understand each and every step. SVM is one of the most important models for the data scientists. Once you are comfortable with all the steps in SVM, you can move on to the next lecture. The next lecture is a project lecture on SVM. We will have a quick overview on the project and then we will move on to the project solution. So see you in the next lecture. Good luck.